2019 AP Physics 1, question number 3. A projectile logic consists of a spring with an attached plate, as shown in figure 1. When the spring is compressed, the plate can be held in place by a pin at any of the three positions A, B, or C. For example, figure 2 shows a steel sphere placed against the plate, which is held in place by a pin at position C. The sphere is launched upon release of the pin. A student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compression distances. The student plans to test the hypothesis by launching the sphere using the launcher. I. State a basic physics principle or law the student can use in designing an experiment to test the hypothesis. So the question asks us to use a basic physics principle. Since it involves a spring, we can use any physics equation that has the spring constant in it, K. So for this one, we're going to use 1/2 kx squared. If you don't know already, this is equal to the spring potential energy. So second part of A, using the principle or law stated in part AI, determine an expression for the spring constant in terms of quantities that can be obtained from measurements made with equipment usually found in a school of physics laboratory. So since we're going to say, once it's compressed, let's say at point A, where it's all spring potential energy and 1/2 kx squared, once it reaches equilibrium, all the energy is kinetic. So using conservation of energy, K is just equal to mv squared divided by x squared. Part B, design an experimental procedure to test the hypothesis in which the student uses a launcher to launch the sphere. Assume equipment usually found in a school physics laboratory is available. In the table below, list the quantities and associated symbols that would be measured in your experiment. Also, list the equipment that would be used to measure each quantity. You do not need to fill in every row. If you need additional rows, you may add them to the space just below the table. So as I said earlier, we're going to be using our energy conversion from the initial spring potential energy into kinetic energy. 1/2 kx squared into 1/2 mv squared. So for our experiment, we're going to have to figure out x, m, and v in order to determine k. So for x, it's the displacement of the spring. And the symbol we can use is x per displacement as shown in this equation. And to measure this, we just simply need a meter stick. So now we have x, we need to find m. And m is just simply the mass. Symbol, as seen in our equation, is just m. And to measure this, we just need a balance. Our last variable is v, so that's velocity. And to measure this, we can just use a photo gauge. Second part of part B. Describe the overall procedure to be used to test the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances, referring to the table. Provide enough detail so that another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. As needed, use the symbols defined in the table and/or include a simple diagram of the setup. So first, we measure the mass of the block using a scale. Then we attach the block to the scale and compress it a distance x, which we use a meter stick to measure. Set up a photo gate at the original uncompressed distance. Then we release it from its compressed position. Record the value displayed by the photo gate when the block passes its equilibrium position. Now repeat the experiment for a variety of compressed distances. Each experiment can also be tested multiple times to ensure accuracy. Part C. Describe how the experimental data can be analyzed to confirm or disconfirm the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances. So after we've completed our experiment, we can take the values and use energy conversion to see if K values stay consistent. K can be found by mv squared divided by x squared, which we stated earlier in the question. If we see that for each compression length, that the K values stay consistent within experimental uncertainty, then it confirms the hypothesis that K doesn't change. Part D. Another student uses a launcher to consecutively launch several spheres that have the same diameter but different masses, one after another. Each sphere is launched from position A. Consider each sphere's launch speed, which is the speed of the sphere at the instant it loses contact with the plate. On the axes below, sketch a graph of launch speed as a function of sphere mass. Okay, so in this instance, we're asked to compare spheres of different mass. So as stated earlier, from energy conversion, we know that at its maximum compressed distance, the spring potential energy, which is 1/2 kx squared, is equal to the maximum kinetic energy at the equilibrium position of the spring. So since they're compressed the same amount, that means the final kinetic energy would be the same as well. So let's take a look at the mass, since the mass is changing. We can see that from the equation of kinetic energy, if mass increases, that means velocity would have to decrease. That means our graphs, when we label launch speed and sphere mass, it has to be downward of some sort. We see that it's not directly related. An increase in mass would decrease velocity squared. That means we'd have to draw a curving down line like this, since this would represent the square relationship of velocity. And that would conclude Part D and the rest of AP Physics 1 2019 free response question number 3.